right, books open to page 184. You answered questions 1 through 3 and 6 through 9 for homework last night. Let's take a look at those as we begin talking on a topic that you wish you knew better, energy. Yes, as we get down to the end of the semester here. Anyone feel like you've got really good energy still? Feel like you'll have a lot better energy after Christmas break? I feel like it probably won't be any better then, but I'm looking forward to Christmas break anyway. Anyway, question number 1 here on page 184. What is the definition of energy? Kendall?
The definition of energy is the capacity to do work.
She actually wasn't that bad. Anyway, the ability to do work. Good. It's a horrible definition, but it's the best we come up with. Hard to define. Write the kinetic energy equation. Audrey?
The kinetic energy equation is KE equals 1/2 mv squared.
Very good. Number 3, what's the relationship between work? Michael. That one.
Okay. Work done is equal to the gain in kinetic energy. The equation is W equals delta KE equals KE final versus KE initial.
Good. That's the relationship between work and kinetic energy, and that was the equation. All right. Number 6, define potential energy. Kendall?
Potential energy is the energy an object acquires when it is exposed to a force.
Excellent. Number 7, what's the equation for gravitational potential energy? And identify each variable, Audrey.
W, which stands for work, equals delta PE, which stands for potential energy, equals mgh sub F minus 0 equals mgh sub F.
Okay, I was just going to go with it. PE equals mgh. You went ahead and equated work to potential energy. But yes, M is
mass,
G is
gravity,
and H is height of the object. Number 8, how is conservation of energy satisfied when you toss a ball into the air? Michael, a little bit longer answer here.
When throwing a ball into the air, the conversion energy is satisfied because the potential energy is converted to kinetic energy.
Okay, I guess that technically answers the question. Anyone have a little bit more detail explaining that at all? No? Okay. Number 9. What's the equation for elastic potential energy, and identify each variable? Kendall.
The equation for elastic potential energy is F equals negative kx, where F is force, and then negative k is the constant of proportionality.
Or the spring constant.
Of the spring constant. And I have no idea what x was.
Well, that's actually just Hooke's law that you gave me. That's actually not the equation for elastic potential energy, but force equals negative spring constant times stretch, which is what the x was. Which, of course, that was used in chapter 10 when we talked about spring motion. That x was that stretch for the spring. How about Audrey? What was the equation for elastic potential energy, and identify each variable?
Potential energy, or PE, equals 1/2 kx squared.
Good. PE sub S equals 1/2 kx squared, where, of course, the PE sub S is the
potential energy.
the elastic potential energy, or spring potential energy, which is sometimes called. The K is the
constant.
and the X is the. Which is that it?
Yeah.
Kendall? The stretch. There we go. All right, next section in your notes. Next section in your notes. That's what we're talking about today, and in our next lesson on Monday. We said that work is defined as a transfer of energy. I do work on the water bottle when I cause it to move, right? Transfer of energy is evidenced by motion. The water bottle was sitting there minding its own business. Now it is moving about, and because it is moving about, that which can move, that which does move, obviously can move, and that which does move and therefore can move must have energy to move. So the bottle is having energy because I am giving it energy. I am doing work, transferring energy into the bottle. We're getting very sleepy. Good to have you back, by the way. I picked on you in some of the videos. You noticed? Okay, I wasn't sure which videos you watched or didn't watch, and I was like, yes, you were answering questions in Audrey and Michael voices in one of the lessons. So you did a very convincing job, by the way. But anyway, if work is a transfer of energy, then what is energy? Well, for me to transfer my energy, and that is doing work, I must therefore possess energy. If I possess energy, I can do work because I then have something to transfer, right? You can give that which you have. You cannot give that which you do not have. So if you can do work, it is because you have energy to transfer. Therefore, energy can be thought of as the ability to do work. It's very circular, isn't it? Work, transfer of energy. So what's energy? The ability to do work. Well, it's work. Right? It's the best we can come up with. Energy is this thing, this what we have, this ability that we have, and when we don't have it, it's sad, right? But the ability that we have to get up and move, the ability to do work. And that's what we're going to write down for our definition of energy. We will abbreviate the term energy using the letters NRG because we're lazy. So NRG is the not any relation to the business or corporation NRG, which owns NRG Stadium in Houston. Energy is the ability to do work. Now, a couple broad categories of energy that you're familiar with already. The first broad category of energy is kinetic energy. Kinetic energy. And you didn't even have to look up kinetic energy in your reading to know what kinetic energy is because you've known it for years. What is kinetic energy, class? Energy of motion, right? Here's how we'll define it. It's the energy an object possesses or demonstrates, one could say. It's the energy an object possesses due to its motion. The energy an object possesses due to its motion. You can also think of it as the energy an object demonstrates due to its motion. Because it is in motion, it obviously has energy. How much energy? However much energy it has based on the motion it's having. For instance, if I walk into class very slowly, one might argue it doesn't look like Mr. Nadaski has very much energy. If I say, oh, students. Oh, you looked better when I closed them. Hello, students. Very talking, very slowly. You'd say, oh, he's not got very much energy. And you'd probably say it's boring and you might fall asleep. But if I walk and talking like this, I'm just moving very quickly. Hey, good to see you, Michael. Good to see you. Audrey, it's great to see you. Then you'd be like, okay, that's a little too much energy, right? Little kids get this way when they have sugar sometimes. Sometimes seniors get this way when they have sugar. Everything's just really happy and everything's just so bubbly and energetic. And I don't actually mind a little energy. It's refreshing when you're teaching seniors, for seniors to have a little energy. But powdered donuts, whatever. Audrey. And so there was one day in pre-calculus that she was just answering everything. She had a big smile on her face. She was just really perky and energetic. And you know, it's 6th hour, the day's winding down, and you know, not that she's, you know, a dull, boring, lifeless student normally. She's just a little extra perky is a good word. And I was like, you seem really perky today. She's like, I had sugar. I had powdered sugar donuts or whatever it was. And anyway, I thought it was funny. So I was telling my wife about it, and she remembered Audrey as a 2nd grader. Many moons ago, back when my wife was, back when Audrey was just a wee thing. And I didn't say it. Picking on my wife, and she's not even watching, I hope. She is a subscriber. By the way, if you're not a subscriber, like, subscribe, ring the bell. Anyway, whatever. And she's like, I remember one time Audrey came in and she was crazy. And so I talked to her aunt, because her aunt taught here years ago. Talked to her aunt, she's like, and yeah, she had chocolate milk. She doesn't normally have chocolate. Maybe it was Fruit Loops or Lucky Charms. Anyway, something sugary. She's like, we don't normally give it to her for that reason. Anyway, but you get that. I had a student who had been in Mrs. Morrison's class, and Mrs. Morrison's a good teacher, but she's a very different style than me. He'd been in Mrs. Morrison's class, and at the semester break, I took over the class because we needed Mrs. Morrison to teach something different. And he's like, his first day, he goes to his mom, and his mom told me the story later. She's like, yeah, it's like Mr. Nadaski's like a wound-up rubber band. He's bouncing everywhere. Man, I don't think of myself as that bouncy necessarily, but I guess comparatively it was more motion, more energy, right? And it's not that I have energy because I'm moving necessarily, but because I am moving, you understand how much energy I have. So it's the energy an object possesses due to its motion, or you could think of it as demonstrates due to its motion. Now, another way to think of this then is the work that is done to the object equals the energy it acquires. So the more motion that we see this bottle demonstrating, right? If it's a slow toss to Michael, versus a fastball to Michael, right? You would see that there was a different amount of energy that was transferred, and based on the motion that you see, tells you how much energy was given to the bottle, correct? Work then can be thought of in a similar note as a change in an object's kinetic energy. Work can be thought of as a change in the object's kinetic energy. For instance, let's take, the bottle was sitting here stationary, it has no kinetic energy, all of a sudden it goes flying through the air at Michael, it all of a sudden does have energy. Work is the change in the energy that the bottle now has, correct? We could also think of it this way, tetherball, right? You familiar with tetherball? You are, you do daycare. All right, and the tetherball is already spinning around, and then you hit it more, and it starts spinning around faster. All right, there was already a certain amount of kinetic energy it must have had, right? And you hit it, you transfer more energy, there's now been a change in its kinetic energy. Work can be thought of as that change in kinetic energy. Therefore, kinetic energy is analogous to work done. Therefore, kinetic energy is going to be measured in joules, just as work was measured in joules. But to figure out kinetic energy, we could relate it back to work. So don't write this down, I just want to kind of take you through a progression. Remember I said work is force times displacement? And we said that force is mass times acceleration. So therefore work, or this change in energy, if you will, can be thought of as mass times acceleration times displacement. Or you could say that work is mad. Displacement, if there's an initial velocity of 0, is v sub I t plus 1 f a t squared. You might recall going way back to chapter 6. But if we assume initial velocity 0, drop the v sub I t, displacement can be thought of as 1/2 a t squared. Pull out the 1/2, combine the two a's to get a squared t squared. We could think of 1/2 m a squared t squared. Or we could think of this as 1/2 m a t squared. But remember, what is acceleration? It's a change in velocity per unit time. Therefore, acceleration times time is velocity. So we could say that this is 1/2 mv squared. And that's our equation for kinetic energy. Because of the way we define the kinetic energy as that energy of motion, the movement of the object, as shown in this equation, allows us to find kinetic energy. So kinetic energy is 1/2 mv squared. Work then, being a change in kinetic energy, would be final kinetic energy minus initial, because after all, change is always final minus initial, right? And therefore we could think of it as 1/2 mv sub f squared minus 1/2 m v sub I squared. If we wanted to calculate work done on an object, find how much kinetic energy it had to start with, find out how much kinetic energy it has now, and when you subtract, that tells you how much work must have been done. So work and kinetic energy obviously very closely tied together. Need to know this equation, need to know kinetic energies in joules, and need to know that work can be thought of as that change in kinetic energy. Look at page 173, if you would, and example 12.1. And we have an unfortunate man who is neither option seems particularly appealing. Read the word problem for us, if you would, Michael.
A bullet with a mass of 10 grams is moving at a speed of 1.0 times 10 to the third meters per second. A ball with a mass of 4e2 kilograms is charging at a speed of 5 meters per second, which has the greater kinetic energy.
All right, so what they did was they plugged in the two kinetic energies into the kinetic energy equation, 1/2 mv squared. So it's 1/2 times the mass of, now it's 10 grams, but you'll notice they made it 0.01 kilograms. Multiplied that by 1,000 meter per second squared. And they found that the kinetic energy of the bullet was 5,000 joules of kinetic energy, meaning that once it hits the man, it could do 5,000 joules of work on the man. Assuming the bullet stops in the man, it will transfer 5,000 joules of energy, which is why a bullet to the heart stops the heart. The heart can't handle that much energy. Bullet to the head shocks the brain. That's why bullets are deadly. Do a lot of work in a very small amount of space. The bull, on the other hand, 400 kilograms and 5 meters per second, which they squared. And you notice that the bull also has energy of 5,000 joules. The difference is the bull will do 5,000 joules of work to the entire body of the man, total mangling, versus just one hole that leaves him dead. He will be mangled and dead. Caught in the middle, they're both bad options. What I want to draw out of this, though, is this. The mass of the bull, let's see, it was 400 kilograms, and the bullet was 10 grams. That's a difference of 40,000 times greater mass. The bull, 40,000 times as much mass as that little bitty bullet. But the bullet was going 1,000 meters per second. The bull was only going 5 meters per second. The bullet was traveling 200 times greater velocity. But the bullet, only 200 times greater velocity, had the exact same amount of energy as something that had 40,000 times more mass. Which then has a greater impact on an object's energy, mass or velocity? Velocity, because it's only 200 times greater, it comes to the same equal. This took 40,000 times greater to make it equal, right? So velocity clearly has the greater impact. You can look at the equation to tell that as well. It's squared, mass isn't. Velocity has a squared effect, if you will, on an object's energy. So if you wanted to impart more energy to an object, you could either use something that has greater mass or greater velocity. I take you to Bugs Bunny. You seen the Bugs Bunny baseball episode? It's a classic. It's a great, great episode. And you remember Bugs Bunny is playing baseball. He's like, yeah, I can beat these guys by myself. There's been a rotation change. Now pitching for the whatever it is. Bugs Bunny, catching Bugs Bunny, first base Bugs Bunny, second base Bugs Bunny. And Bugs Bunny plays all the positions. And so he throws the baseball, and all the guys are striking out, and he starts hitting home runs, and he starts catching up. And he throws the slow ball, remember? And the first guy swings 3 times and misses at the same pitch. The next guy also swings 3 times and misses, and then strikes all 3 guys on one pitch. It was great. And then the one guy comes up, the big guy comes up, remember? And he knocks down a tree. And now he's swinging a tree. Well, a tree would have greater mass, wouldn't it? And if he's able to swing that tree because it has greater mass, it would do more work. It would impart more energy on the baseball. And he hits the baseball, remember, and it goes flying. And he has to run out of the ballpark, and he gets in a taxi, and he climbs up to the top of the Statue of Liberty, and he catches the baseball. Or whatever, I think it was that. It might have been Empire State Building. And the Statue of Liberty calls him out because he caught the ball. Anyway, and great episode. But how practical is that? A bigger bat will impart more energy. So why is it that there's this desire for a lighter bat? Why is the drive, how can I make my bat lighter? Why not make it heavier? Heavier would impart more energy, wouldn't it? Because if the bat's lighter, you can swing it faster. You want fast more so than heavy. So the picture there of the golfer, right? Technically, a massively heavy golf club, if you could hit the ball and not, leave enormous divots or craters on the green or on the driving range, would actually send a golf ball further. But it would be better to use a lighter club that you can swing around faster. Does that make sense? So velocity has the greater impact on the kinetic energy. Now, I want you to think about this for just a moment, because kinetic energy or work are related in this sense as well. Let's suppose the bull is charging the man, and the man does the right thing and hops the fence. And the bull, having so much momentum, which we're going to talk about later, crashes into the fence and comes to a stop. The fence, if it stopped the bull, caused a change in velocity, caused a deceleration. And we know that velocity only changes when there's an outside force. So if the bull crashes into the fence and stops, the fence did work on the bull by exerting a force this way. The bull's motion would have been this way. So therefore, the work that the fence did would be negative work, correct? Because the force of the fence was opposite motion. Negative work done by fence. Here's another way to think about it. When the bull comes charging, the bull has energy, correct? Crashes into fence and stops. Theoretically, if it's a strong fence. Crashes into the fence and stops, right? Did the bull gain or lose energy by crashing into the fence? He lost energy by crashing into the fence. Therefore, negative work is done because negative work causes a loss of energy. If work is a change in energy, a positive change in energy would be positive work. A negative change in energy would be negative work. Now, realistically speaking, if it's that fence that you see in the picture, bull crashes into fence and fence splinters. Now, bull gets bad headache and bull probably wonders what's happening and stops anyway. Still negative work done by fence. Fence was motionless. All of a sudden, fragments of fence go flying. Fragments of fence suddenly have energy. Where did they get the energy from? The bull. So did the bull do positive or negative work? positive work, because he caused that which had no energy to have energy as it goes flying. Does that make sense? So oftentimes what you'll see is if two objects collide, one does positive work, the other does negative work. Turn the page and look at example 12.2 on page 174. Read that example problem for us if you would, Kendall.
A hammer with an initial velocity of 9.3 meters per second hits the nail. The hammer weighs 0.50 kilograms. How much work does it do in driving the nail into a piece of wood?
By the way, cross out where it says weighs, has a mass of. It doesn't weigh 0.5 kilograms, it has a mass of 0.5 kilograms. Now, that means hammer, initial velocity of 9.2 meters per second. All right? And so we swing the hammer, it hits the nail. What does the nail do? Hopefully, if it doesn't bend. How many of you inevitably bend nails when you hammer them? Yeah, I've done quite a bit of hammering nails, and I still bend the nail probably 1 out of every 4 times. Hitting it square, I don't know what my deal is. Anyway, that's why they make nail guns. Or if you're like me, use a power screwdriver and just use screws. Because that way you can back them out easier anyway, right? Nail, you have to pry it out. Screws, back it right out. Anyway, so hammer hits nail. Nail was sitting there on the piece of wood motionless, and suddenly the nail moves, correct? As nail moves, the nail must have gotten energy, enough energy to overcome quite a bit of friction from that wood, correct? As it dives into it. What does the nail do to the hammer? Bam! It stops the hammer, doesn't it? Hammer had energy. Hammer loses all of its energy because all of that energy then transfers into the nail, correct? If I wanted to find the energy change of the nail, I would need to know mass times velocity squared of the nail. But I don't know that. What I can do is figure out how much energy the hammer loses, and that's the energy that transfers into the nail. Now, technically, some energy is lost to sound energy, okay? We're not going to get into that right now. What we can do is simply look at the hammer's energy lost, and that is the energy that is gained by the nail. All right, so to find work, since it's a change in energy, we can take the hammer's energy. The hammer has a mass class of 0.5 kilograms, and that's going to be in both cases. The velocity of the hammer initially was
9.2 meters per second.
9.2 meters per second. We're going to square that. After the hammer hits the nail, hammer comes to stop. What's the hammer's velocity after it hits the nail? 0. So you'll notice that the final kinetic energy of the hammer is 0, right? Anytime you multiply 0 squared, it's still going to be 0, right? So really all we'd have to do is find this. And this tells what the change in energy is of the hammer. All right? Multiply. The 1/2, the 0.5, which is also a half, times the 9.2 squared. What is the energy change of the hammer?
Negative 21.16.
Joules. Negative 21.16 joules of energy that the hammer loses. How does it lose energy? By transferring the energy into the nail. What do we call the transfer of energy? Work. So if it gave up this many joules, then that's how much work it did. 21.16 joules, or rounded as you see there, 21 joules of work. Does that make sense? The hammer lost energy, gave up energy. Not like in the stupid last Star Wars episode where this life force and giving up. Not like that kind of energy. Okay, so 21 joules, our answer here. Turn over to page 185. Turn over to page 185. Let's look at a couple of more problems here. Problem number 1 on page 185, and Audrey, read it for us.
A sports car weighs 8,110 newtons. Find the kinetic energy when traveling with a speed of 30 meters per second.
All right, how do I find kinetic energy, Audrey?
KE equals 1/2 mv squared.
KE equals 1/2 mv squared. What numbers do they give me in this problem?
It weighs, so
They give me the weight of,
8,110 newtons.
what other numbers do they give me?
The speed of 30 meters per second.
30 point or just 30?
30.0 meters per second.
All right, and so for my equation, obviously the V, I'm good, right? I can plug that in here, but I can't plug in the weight, class, because it needs the mass. How do I go from weight to mass, class? Divide out gravity. So what is the mass of this car?
827.551.
There we go, that many kilograms. So take that value, I'd multiply the half, or 0.5, and then I'd multiply the velocity squared. And how much kinetic energy does this car have as it races down the road at 65 miles an hour? 0.9, blah, 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 right? Let's go scientific notation, because that's easier. And how many joules of energy? Second function, SCIs, that's the 5 button for you two ladies. Michael, it's a little bit different for you, but
3.72 e to the 5.
E5 joules. We say 3.72 E5 joules is our answer. Not wrong to say 372,000 joules or 372 kilojoules, but big number, like, I don't want to think about it, second function, scientific notation. Questions number 1. Number 3, go and read that one for us, Michael.
A mass of 5 kilograms initially at rest on a frictionless surface is given a speed of 14 meters per second. What is this change in kinetic energy and how much work is done on the mass to accelerate it?
All right, just part A at your seats. Find the change in kinetic energy. We haven't needed this much this year, but we're going to as we move forward. Anytime we have a change in anything, change always means final minus initial. Class, what does change mean? So this literally means take the final kinetic energy and subtract the initial kinetic energy. But thoughts on the initial? It was at rest. It's 0. It had no kinetic energy. So really all we have to do is find how much energy it has when it ends up. So for that, 1/2 m v sub f squared. You plug in the numbers, the 1/2, the 5, and the 14 squared. And Michael, how much kinetic energy does it have now? What is its change in kinetic energy? 490 energy measured in? Joules, the same thing that work is measured in. How many got the 490 joules of energy for the change in kinetic? Now the next part of the problem, Michael, read it again, said...
How much work is done to the mass to accelerate it?
Thoughts, anybody? 490 joules. If that's what the energy changes, then that is also the work. So that's the change in kinetic energy. That is also the work, because work is a change in kinetic energy. They were making that point by re-asking for the work. Questions on that? Number 5. Building on problem number 3 here. Read that second part, Kendall.
In problem 3, the applied force is 15.7 newtons. Calculate the distance over which the force acts.
So it says that the force that's applied, there's this 5 kilogram thing on a frictionless surface, and the force that acts on that is 15.7 newtons. The question is, over what distance did that force act? So I'm given a force, I'm asking for a distance, and I know the work. Well, go back to chapter 11. What's my formula for work, class? So it's not wrong to calculate work as a change in kinetic energy, but it's still not wrong to calculate as force times displacement. So if the work is 490 joules, and there was a force of 15.7 newtons, over what distance did that force apparently act?
31.2.
And is it 3 sig figs or 2? 2 sig figs. So 31. 31 meters for distance. 31 meters of distance, apparently. Questions on that? Again, do we see how we can connect the old work equation with the new work equation? They all relate together. Any questions on that? Let's talk about potential energy next. Next thing in your notes, potential energy. Potential energy is defined as the energy an object acquires. The energy an object acquires when it is exposed to a force. The energy that an object acquires when it is exposed to a force. Now, we often think of potential energy as energy of position. Based on the position the object is in, it has however much potential energy. But the reason for the position mattering is if an object is exposed to a force, yet the force does not yet act, right? Then we have what's called potential energy. The most common example would be gravitational potential energy. But for instance, when the object is right here, now we would say it has potential energy. Why? Because it has the ability, with just the slightest little bit of force right there, pulling it down, to suddenly move, right? It has no kinetic energy right now, but there's the potential for it to have kinetic energy, right? When a preacher in chapel says, I look around this room, I see so much potential. What is he saying? You ain't done nothing yet, but you could. Okay, hopefully that's not true. You're in an age where you could and should be doing some things for the Lord. But what he's saying is, I see the potential. I see that you could do something great if you just stopped being a lazy slob and did what I said. Anyway, so there's the potential for it to move. It hasn't moved yet, but just a little force. And now it moves. It was exposed to the force of gravity. If gravity hadn't acted on it until I gave it that little extra nudge. In a similar sense, oh, I busted it. All right, in a similar sense, let's not get that on the iPad or on the phone or whatever. It'll dry. Let's take the leaky water bottle. It hasn't actually moved yet, but it's exposed to a force. Now, it's going to be really hard mathematically to calculate how much force it's exposed to. So we won't get into all the different types, but I mean, anytime there's a force waiting to act, we would say that there is potential energy. If I pull back a rubber band, I'll have one tomorrow, or Monday when we come back. If I have a rubber band and I pull it back, it hasn't acted yet, but there's potential. If I just let go, it could fire, right? And it could move. It would be free to move and demonstrate its kinetic energy, to live up to its potential, right? When there's that force present waiting to act, you pull something back in a slingshot, right? There's potential energy there. So it's the energy an object acquires when it is exposed to a force. What we will typically think of for potential energy, which we'll notate PE, is oftentimes we think of gravitational potential energy. Gravitational potential energy. Simply because, again, as the water bottle is held aloft, hi Kendall, just kidding. As the water bottle is held aloft, the slightly leaky water bottle is held aloft, it would just take me letting go or the friction slowly slipping for gravity to act, right? Technically gravity is acting, it is moving, it already has a little bit of kinetic, but as I'm holding it here, just letting go would cause gravitational force to act on it. It's exposed to the force, it just hasn't acted yet. Now, if I held it lower, it wouldn't be able to fall as far, would it? And remember that the object's going to accelerate the longer it's in the air. Well, it's not going to be in the air very long if I hold it down here. Or if I held it just above the floor, there's not really the ability for gravity to act much. It has less potential. So as the speaker looks out over the auditorium and he sees somebody that he realizes, yeah, bless him, that kid's just, the shirt's untucked, the hair's all disheveled, he hasn't showered in 3 days and he reeks, and it's like, yeah, I don't see a lot of potential there. Well, why would, admittedly, the preacher wouldn't say that. But, judgmental humans that we are, we might even think that, right? Say, man, there needs to be a change in that person. Why? Because we just don't see the potential, right? A sharp-dressed, clean-cut, well-groomed young man, on the other hand, like somebody like Michael, for instance, you'll always say, man, that guy could do something great. Why? Because he's done the things necessary in his life to achieve greatness, right? Somebody who can't take care of his own hair, can't brush his teeth, can't dress sharp. You look at it like, yeah, what a bum. Okay, that person's not going to amount to much. Why? Because they haven't put themselves in a position to achieve greatness. Well, if this thing is just barely above the counter, gravity couldn't do much with that, right? It wasn't in a position to achieve much. But the higher it goes, the more that gravity can act, the more velocity it can attain with its mass. That is to say, the more kinetic energy it could demonstrate. So really for gravitational potential energy, really the only key is gravity has to act on the object's mass with a force of weight, mass times gravity, and the greater the height the object is at, the greater potential is there. So gravitational potential energy is simply found in this equation, PE equals mgh. The mg is the force that would act on it. It's exposed to a force. And the height is the distance through which the object would be able to be acted upon. After all, we said that energy is what is transferred through work. Work is force times displacement. So of course we could think of work not just as a change in kinetic energy. Work could also be thought of as a change in potential energy, or mg delta h. Work can be thought of as a change in potential energy as well. Now, admittedly, when I change the potential energy of this object, I am lifting it, correct? There's a force acting on it, raising it to a height. It took work to do that, therefore I transferred my energy into the bottle, which caused it to move. But even though it is not moving, because its potential energy has been changed, work has been done in the past tense. And then I let go, crashes and busts all the way open, and I gotta get a mop and I'm too lazy, so I'm gonna do that. Now, you've heard it throughout your life about the conservation of energy, right? That energy can't be created nor destroyed. It can only be transferred or converted in form. Well, if we took something like Miss Morse's soft foam dye that she got from orientaltrading.com, who does not sponsor my channel, so I don't know why I'm mentioning this, but if we were to take this green dye and were to toss it into the air, as it leaves my hand, remember, it leaves with a certain initial velocity. Well, what's going to happen as it travels upward? It's going to slow down, slow down, slow down, slow down, until at some point it stops, right? So I toss it up, and right up there it stopped, didn't it? And so if it's slowing down, remember kinetic energy, 1/2 mv squared, as it leaves my hand, it has a greater velocity. As it rises, it loses velocity. Therefore, it is losing what? Kinetic energy, correct? But as it leaves my hand, although it's losing kinetic energy, it's rising higher and higher, which means it's gaining potential energy. So it leaves my hand with a certain amount of energy, and it's all kinetic energy out of the hand. As it leaves my hand, it rises until it gets to the high point, where it has now lost all of its kinetic energy. Velocity 0. But it has reached its maximum potential energy. And then it begins to fall back down. Well, as it falls, it's losing height, meaning it's losing what? Potential energy. But as it's falling, although it's losing potential energy, this is true of any falling object, although it's losing potential energy, what's it doing as it's falling? It's getting faster, 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 faster. It's increasing its velocity. So as it falls, although it's losing potential, it's increasing in kinetic. And the total energy between the two of them stays constant. So conservation of energy is satisfied because kinetic and potential can kind of go back and forth. And that's true of a falling object, a rising object, any object that's changing in its potential. Now, if the object's moving horizontally, here it's just friction, it's eating up, right? So I give it energy, and the energy gets lost through friction. We're going to get to that probably in our next lesson. So conservation of energy is still true. Look at page 175, example 12.3. Page 175, example 12.3 readeth that for us, Audrey.
An elevator weighing 1,500 pounds rises 1,400 feet as it goes from the ground floor to the top of Willis Tower. in Chicago, what is the change in gravitational potential energy?
Okay, so let's see. 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 Yeah, I don't know. If it's a glass elevator, I ain't getting in it. I don't need to see 1,400 feet below me. I just, where I went to college, the academic, one of their two major academic buildings with classrooms and stuff, everything else had other purposes, but really just two academic buildings. And the elevators had glass enclosure, kind of like they do at the mall. Mall is 2 stories. I'm good with 2 stories. I was good with 4 stories, 5 stories. My stomach, by the 6th floor, it also felt like the elevator shook a little bit up at floor number 6, which was the highest floor. I didn't go up there very often, but 6th floor, that elevator, I didn't care to look at. I don't do heights too good. So as long as it's an enclosed elevator, though, I don't go up 30 floors. I don't care. I just stand in there as long as I don't have to see what I'm doing. Anyway, weighs 1,500 pounds. Well, if it weighs 1,500 pounds, that's the mass times gravity. And if it rises 1,400 feet, that's the change in height. So how do we find the potential energy? Just multiply the weight times the height, right? You could also think of it as work done, right? There's work done by a motor that causes it to go up, correct? And a machine, inevitably, right? And a pulley system, block and tackle probably worked in there. But there's a certain amount of work being done to raise this thing up. Well, the force that's applied would match whatever the force of weight is. That would be the force applied upward. Times displacement, that's the 1,400 feet. So you can think of it as W equals FD. You can think of it as P equals mgh. The mg, though, collectively is the weight. So if it weighs 1,500 lugs and it rises 1,400, then how much potential energy does it have? At your seats. I feel like I should be able to multiply these 2 numbers in my head, but calculator, here we come.
2.1 E6.
And now it's not going to be joules this time, though, is it? It's going to be what? Foot-pounds. Again, that's what we use in the U.S. for work. That's also what we would use in the U.S. for energy. How much energy does an object have based on foot-pounds here in the U.S.? We will primarily, though, use joules in this class, but there's an example of using foot-pounds. Questions on that? Turn over to page 185. Let's take a look at a couple of problems on these pages as well. Problem number 6. Go ahead and read that if you would. Michael.
Suppose a 3.86 kilogram brick falls from 7 meters to the ground. Is the work done by the ground positive or negative? Is the work done by gravity positive or negative? And find the work done by the ground on the brick.
All right, so let's start with a couple of questions. Brick is falling, and it hits the ground and probably busts into shards, okay? But regardless, it hits the ground, and what happens to the brick? It stops. Even if it doesn't bust into pieces, it stops, right? Did the brick gain or lose energy as it hits the ground? It instantly lost. Think about it. When it was high up, it had a lot of potential energy. And gradually, as it fell, it lost more and more potential, but it was gaining kinetic as it went faster and faster, correct? So the total energy was staying the same until it hits the ground. And at the ground, what's its potential? 0, because it's a 0 height. But if it also stops moving because it hits the ground, what's its kinetic? Suddenly, 0. So is the ground doing positive or negative work to stop the brick? It's doing negative work because it's taking the energy. Either it's really soft, soppy ground, swampy type ground where it hits and squelch and it just sits there in the mud and the ground absorbs all of that energy from the brick. Either way, the brick lost energy. Or if it busts into pieces, the energy is used to shatter the brick and then the pieces lie there with no more energy and still energy has been lost from the brick. So the ground does negative work. Does gravity do positive or negative work on the brick? Positive work, because it's because of gravity. Like if there were no gravity, the brick just sort of hovers there and does nothing. But because there's gravity, brick falls and gains energy, correct? Gravity is what gave the brick its energy. The question is, find the work done by the ground on the brick. So we already said the work that we get is going to be negative, right? We could try to find this as a change in kinetic energy. I don't want to. It's easier to find this as a change of potential energy. We'll take the mass of the brick, class, kilograms, which that's a pretty solid brick there. Gravity.
9.8.
We'll assume 9.80 meters per second squared. And then what is the change in height going to be for this brick? 7 meters. But remember, work is always final minus initial, correct? The initial height was 7 meters. The final height is 0. What is the change in height? To go from 7 down to 0. That's a change of -7 meters, which is why the work done by the ground is going to be negative. And how much work do we have done?
264 point.
I typed something wrong. Yeah, what did you say?
264.796.
Okay, and then round it off to 3 sig figs?
265.
Yes, it is 3 sig figs. 265 joules of work done. But since it stopped the brick, since it took energy from the brick, negative 265 joules. That make sense? Look at problem number 8. And read that one for us if you would, Kendall.
On a family vacation, you drive from the seashore to the top of Pikes Peak, 4,320 meters. Your car weighs 8,890 newtons with your luggage and family in it. What is the change in the car's gravitational potential energy?
All right, so we're going from seashore, which means sea level, elevation 0, up to Pikes Peak. Now, obviously there's going to be a drive to get there because Pikes Peak is not at the seashore, okay? So you're driving, but we're only looking at a change in gravitational potential energy. And the 3 things that affect gravitational potential energy, class, are? The mass of the car presumably does not change too much. I mean, well, we started with a full tank of gas, we got there, it was empty, so, okay, whatever. The mass pretty much doesn't change. Gravity technically changes, but we're going to go into that little detail. And so really the only factor we have to account for is the change in height, correct? We went from the seashore, which was 0, up to Pikes Peak, which was what, Kendall?
4,320.
So at your seats, find the change in gravitational potential energy. Oh, they don't give us the mass, do they? What do they give us?
Weight.
The weight. Do we need to divide by gravity? No. Because if we did divide by gravity, the mass, what would we do right after that?
Times.
Multiply the gravity back in. So remember, you can substitute weight times the change in height for that change in potential energy. So just type the 2 numbers. Now, is this a positive change in height or a negative change in height, class? Initially 0, final at 4,320. That's a positive change, right? We're increasing the height. So we're increasing the gravitational potential energy. It's a big number, Kendall. How much is the change in potential energy?
3.84048E7.
Okay, so we'll round it off to, I think it was 3 sig figs, 3.84 E7 joules is the change in gravitational potential energy. Not necessarily work done, okay, but it was change in potential energy. There was also, a velocity that it traveled with, so there was work done to all that, but just looking at change in gravitational potential energy. Questions on that? All right, your homework for the weekend is to read pages 174 to 175. So, wait, only 2 pages? What is wrong with me? Read pages 174 to 175. Fact checking my page numbers here. Should be a 178. So that can't be right. Read pages 174 to 178. Fact checker got me. On pages 184 to 185, you wouldn't find these answers on the other. On pages 184 to 185, answer questions 13, 14, 16, 17. Page 184 to 185, answer questions 13, 14, 16, and 17, and do problems 2 and 7. Answer questions 13, 14, 16, 17, and do problems 2 and 7. We're going to pick up with this discussion of energy in our next lesson. Have a wonderful rest of your day and a wonderful weekend, and you are dismissed.